In this part, we will prove some properties of the Splay trees using the access lemma. We had these 5 properties in the beginning. In this lecture I will prove balanced and entropy and static optimality. In the exercise sheet you will have to prove the working set property, and the dynamic finger you can also do if you want. So before we do that, we still have to look at one more thing. And that is, we are always talking about querying sequences here, and that's the important part, because otherwise our amortized analysis does not really work out. So we have a sequence of queries S, and again we have to ask, what is the real cost if we query this whole thing, because that's what it comes down to. I mean, we can prove with a potential method what is the amortized running time of a single step, but if we only have one step, then you cannot amortize with something. So you always have to look at the real cost over a sequence if you use the amortized analysis with a potential function. So let's say that after query k, this is our potential, then the total cost in the end is the potential at the beginning minus the potential at the end plus the sum of the amortized costs. In our example earlier with the stack with multipop, this was clearly a 0 and this was at most n, so we had some clear bounds, but here it's not so clear. We have no idea how the tree looks like at the beginning, so we don't know what the potential is. But we have to figure out by how much does the difference between the potential in the beginning and the potential at the end decrease. Well, this sounds a bit weird. So we have to add something to the amortized cost if the potential gets lower. We said a lower potential for us is better because the tree is more balanced. So why is it bad if the whole thing becomes lower? Well, on the other hand, we said whenever we do a lot of work, the potential decreases. Whenever we do little work, the potential increases. So if the potential decreased, that means we've done a lot of work. So we've done more work than we accounted for here in the amortized running time. And if the potential increases, well, that means we didn't do a lot of work. So we overestimated here. So if we just sum up the amortized costs, then we still have to figure out how did the potential change to get the total cost. Now here's the question for you. Can you give me a bound on this? Well, we have that the sum of weights in every node is at least the weight of the node. So that gives us an easy bound for the end, because the potential cannot be smaller than the sum of the log of the weights. Actually, this is a greater as long as we have at least 2 nodes. So we only get this if our tree is just a bunch of leaves that are not connected. So this is not realistic, but at least it's a lower bound on this. And in the beginning, how large can it be? Well, we will again overestimate. So the sum of weights in the root is log capital W. So let's just assume that all the vertices are the root. This is of course not feasible, but if we move them down, the potential only goes down. So the potential can never be larger than the sum of log of this W. And this is for all the vertices in the tree. So this here is basically n times log capital W. So this bound here is at most, if we sum up over all vertices in the tree, log W minus log W of x. And this should look familiar to you, because this shows up in the analysis of the Splay function in the access lemma. So the change in the potential is as much as we would take time to splay every vertex once. So as long as every key is queried at least once, this one here is at most this one, so the asymptotic running time does not change from the amortized to the real. In fact, you can even show it if you query at least n keys. So now we want to use this whole thing to prove all these lemmas. And what we have to do is we just have to find weight functions. So for every property, we want to find a function that assigns some weight to every key. And the weight that we assign, that depends on the property we want to show. But the beauty of the Splay tree is that the algorithm does not change. It's always the same algorithm. You always do just these rotations. It doesn't care about the weights. But you only change the analysis with these weights. So if I use 1 for all of them, or one of them gets n, everybody else gets 0, it's still the same algorithm. But since the access lemma works for any weight function, we can always apply the access lemma to get some upper bound on the amortized cost. And we will start with doing that for the balance property, which is the easiest. Here we want to show that if we have at least n queries, then the amortized cost of any query is in order of log n. And to do that, we just assign the weight of 1 to every key. Then the sum of weights is an n, and to query something we have to find it and then to splay it. And finding it costs at most as much as playing it, so we can just say a query costs as much as play of x. Now the total time we spent is the change in the potential plus the amortized cost of the splay operations. And this we found out on the previous page. This is just log capital W minus log small w of all of them. And if we plug in these numbers, this is an n, this is a 1, so this here becomes a 0. This is just n log n. For this, we apply the access lemma, so we plug in this term. And again, this is an n, this is always a 1, so this here is always 3 log n. So we sum up the 1 s times the 3 log n s times, so we get n log n plus s from here, plus 3s log n from here. And then we have said we have at least n queries in total, so this is at least n, so the whole term here is in order of s log n. And that means amortized, we require only order of log n time. And this proves the balance lemma. How about the next one, the entropy lemma? We want to prove that the entropy property holds, so the queries take expected that much time that depends on the probability. And now the funny thing is, we don't even change the tree depending on these probabilities. It doesn't matter to the Splay tree what these probabilities are. It just automatically works by splaying the stuff. And you can intuitively say that if something has a high probability, then it will be very close to the top anyway, because you query it a lot of the times, you always move it to the top, so whenever you query it again, it's still very close, so you don't take much time. So we want to prove that we have the entropy property. That means again we have to assign some weights to the nodes. Which weights would you pick? It's very simple, we just take the probability as the weight. So we only use the probabilities for the analysis, but not for the tree itself. Now the sum of the weights is a 1, and we get the amortized cost from the access lemma. So if we want to query key xi, then that takes at most this much time amortized. This is a 1, this is a pi. So we have 1 plus 3 log 1 over pi for each of them. And we can use the log functions again. This is 1 minus 3 log. And now, if we look at the whole thing, well, this has a probability of pi to be queried. So the expected query time in total is, we sum up all these multiplied with the probability. And now the sum of the pi's is 1, so we can pull this 1 out here, and we get exactly this term. There's still a 3 here, but that doesn't matter because we're in the asymptotic bound, so we can just remove the constant, and we have proven the entropy property. And the last one we want to show is the static optimality. Well, there are a few ways to prove this. One of them is, well, you know what the sequence is, so you just check the probabilities in the sequence, like here, and apply them to them, plug this whole thing in, and then it kind of follows from the entropy property. But there's some hand waving in that. So I will show you another proof. We will look at the optimal static tree with the shortest query time for the sequence. So like we had in the beginning, it's this one. And now I want to assign weights depending on this tree. Note that we can do this because we only use the weights for the analysis. We could not do this if we have to use the weights for the algorithm because we don't know this tree. Otherwise we could just use it. So we will just use them for the analysis. So let's say we have some vertex here in this tree, and we count how many vertices are on the path to it in this tree. So basically, what is the level? And then we assign as weight 3 to the minus fi. This is a weird number, but if you plug this in, then everything will work out beautifully. So if we sum all of those up, then this is at most 1. This is very easy to see. In fact, it's always less than 1 unless you have an infinite number of vertices. And now, one splay step takes, by the access lemma, this much time amortized. So when we plug this in, this is a 1, this is a 3 to the minus fi, so this whole thing becomes 3 to the fi. And now we use the logarithm rules, we pull the fi out, then we have 1 plus 3 fi log 3, and this is a constant, this is a constant, we get to order of fi. And this is also the time that you take in the optimum tree. So for every query, the time that we require in the Splay tree is asymptotically not higher than the one that we need in this optimum tree. Again, this is only if you have enough queries, so you need at least n queries. Otherwise, the whole thing will not work out because the potential change might be too large. So this is something you have to keep in mind. But this gives us the static optimality of Splay trees, and this is a beautiful result. That you have this one tree that can change itself, but for any sequence that you give me, it's the best, or asymptotically the best. No matter what sequence you give me. You can even give me a terrible tree and a terribly designed sequence for this tree. And still, asymptotically it will perform as well as any static tree that you can choose for the sequence. So this is an amazing tree and an amazing property. So there's one weakness with this amazing property, and that is this statically. So it's a bit unfair that we're allowed to use a tree and change it, but we compare it to a tree is not allowed to change. So the question is, what if this is not a static tree but also a dynamic one? So the task you have is you create a sequence and you create the best dynamic tree. So you tell the tree, okay, you look like this in the beginning, and after that query you do these rotations, after that you do these rotations, and then you get the best one with the fastest query time. And then you compare it to what the Splay tree does. And this is called the dynamic optimality. So we take the optimal dynamic tree with the shortest query time, and we say a binary search tree is dynamically optimal if it takes amortized not asymptotically more time than this tree for any sequence. And for Splay trees, what we know is it takes logarithmic time more. Well, it does not take more than logarithmic time more. So it's somewhere within this bound. So we cannot show that it's dynamically optimal, but we can show that it reaches this one here. For that, there are some maybe better trees, which are the so-called tango trees. There, the main et al. Could show that it's only a log-log factor away. That doesn't mean that they are better than splay trees. It only means that the analysis is better so far. And the open problem is there a dynamically optimal binary search tree? We don't know of any, but we also don't know if it's impossible. And in fact, many people have the conjecture that splay trees are indeed dynamically optimal, and we just haven't found the proof to it yet. Because it's not so easy to prove some bounds on what this dynamically optimal tree does. And this is probably one of the biggest open problems in algorithm. Find some dynamically optimal BST, or even prove that splay trees are dynamically optimal. Thank you for watching, and I hope to see you again soon.